Hello, class. Welcome to this week's lesson. This is going to be a short one. I know that we don't. I am out of town, so I don't. I don't have a lot of things to really follow up on. We will review the assignments as well as the exam when I come back from break. When I come back from the funeral. So yeah, we'll continue with that. But for this week, it'll just be a short lecture, and hopefully, just shoot me an email if you guys have any questions, or in regards to the lecture, or your homework especially. I know that I've been quite busy, so I haven't had a chance to really respond to some of the emails you guys sent out. But yeah, I'll try my best. I am going to be back this week after today. So on Wednesday I should be returning, so I should be able to follow up with any questions that you guys have. Having said that, we can just get started, and we'll jump right into the lecture, and then after that, I do have a couple things that we have to touch up on before we actually start. Let's look at the syllabus first. Oh man, this is up so high. So based on the syllabus, we should be having a quiz for this week. So we'll have that, and then assignment 4 is due this week. Assignment 5 will be handed out, and I'll get all that set up and ready for you to go with on D2L. You do have 2 weeks for it, so I should be able to post that up by tomorrow. And once I do that, you guys should be able to start on it. You do have 1.5 weeks for it, so there should be plenty of time for you to wrap it up before it's due. And if there's any issues with that, I could extend the due date as well. So just keep that in mind and don't stress out on it. Because assignment 6 does take up a whole 3 weeks, so it'll probably the due date will probably be pushed up to that to April 12th. So I'll see what I can do with that timeline. But for now, So the only thing left is quiz 4 today, and I think I'm just gonna postpone that till next week too. So based on this, based on syllabus, the schedule's going to change a little bit. So really this week all we'll have is just this lecture, and then we'll continue with class as normal the following weeks after that. All right. So having said all that, we'll jump right into the lecture, and then like I said, and if you have any questions, go ahead and email me, and we can go from there. Okay. All right. So this week, last week we discussed about transaction management and how that plays into database. Instead of playing into the database, how that is a crucial part in maintaining concurrency within the system, right, within the database, and why it's so important that any RDBMS has to have a transaction system in order to maintain the concurrency of the data within that database. This week we're going to talk about concurrency control and basically how that transaction management system maintains that concurrency, and it's really through a series of various algorithms that's built into the database to really maintain that. This week we're going to be covering chapter 18. Chapter 18, section 18.1 and 18.2. So we did see in the last lecture that one of the fundamental properties of a transaction is isolation. And when several transactions execute concurrently in the database, however, that isolation property may no longer be preserved. Which is basically timing, right? So when you try to write 2 different things to a database, the timing is very important, and the database can't obviously have 2 different states at the same time. So that state has to be managed somehow, and that's where concurrency control comes in, and the transaction manager is supposed to do that. Okay. So when several transactions So to ensure that it is, the system must control the interaction among the concurrent transactions. This control is achieved through a variety of mechanisms called concurrency control. One of the variety of mechanisms. Let's hold up. Let me adjust some things here. Okay, one of the variety mechanisms that concurrency control falls under is called a concurrency control scheme. So in this lecture this week, in this lecture we consider the management of concurrently executing transactions, and we ignore failures. So in the next lecture, we'll see how the system can recover from failures. As we shall see, there are a variety of concurrency control schemes. No one scheme is clearly the best. Each one has its advantages, but in practice, the most frequently used schemes are two-phase locking, and also the snapshot isolation. And we'll talk about those as we go throughout the lecture. So let's start reviewing isolation levels, right? So SQL 92 transaction levels are specified by the SQL standard. And are as follows. One, that is serializable. And this usually means it ensures serializable execution. However, as we shall explain it shortly. Some databases systems implement this isolation level in a manner that may, in certain cases, allow non-serial executions, and this depends on the RDBMS that you're using, right? So each relational database system kind of implements it a little bit differently, but in the end, the idea is to ensure that every execution is serializable. The next concept is repeatable read, right? So this means that the database allows only committed data to be read, and further requires that between two reads of the data by a transaction, no other transaction is allowed to update it. So in other words, it locks the transaction, and it disables it from updating to it until, well, not really disable it, but it holds it in place until the read is complete before you can do an update to it. So, for instance, when a query is searching the data for some query that needs to be returned to the user, that locks the table and prevents the database from being updated. The data in the database from being updated, and this could lead to certain things. If you don't handle it right in your UI software, it could lead to table lock errors and things like that, and the software itself has to be smart enough to handle that, right? To handle the different table locks that could occur. So when you actually dive into programming UI interfaces for databases, this becomes really important that you understand that table locks can occur, especially if you're doing like a huge search algorithm towards your data, and the query that you're doing that you're executing to do a search is not optimized. It can lead to a lot of different issues, such as table locks, as I mentioned. So the next piece of this is recommitted. Okay, recommitted means that recommitted just means that it only allows the database only allows for committed data to be read, but does not require repeatable reads. So, for instance, between two reads of the data by one transaction, another transaction may have an updated data item and committed, but that data is not reflected on the recommitted, right? So, in other words, only data that's been through the process of verification along with validation among the committed data within let's say your piece of software itself writes the data and does a commit to the database. That's the only time that the data can be persisted to something that's trying to read it. But without that commitment that's in the database, any other reads to that database will not see it. So it has an abstraction layer that limits the capability, limits the ability for the user, for any other users that are using other transactions to really look at data that's in the process of updating. And the very last thing that we're going to cover is the read uncommitted isolation level, right? So when we say read uncommitted, we're saying that we don't care if the data has been committed to the database. We want to read it anyways. And the real drawback, there's a lot of power to this because you can see live updates and things like that. But the real drawback to this is that you will see junk data. In other words, data that's in the middle of transaction that's not complete. So meaning that you're missing certain pieces of that data. And now this isn't when you look at data from a 30,000 feet view, and you're looking at the overall data, a lot of this doesn't really matter. Right? A lot of the details don't really matter. But if you're looking at data at a really detailed level, then this becomes a problem, right? Because some pieces of the data doesn't get updated yet, and you're already trying to read from it, and so you'll end up with partial views, right? So yeah. There's a reasoning behind using read committed and read uncommitted because it depends on the business objectives, right? So if you let's say you just want to view like quantified data, data about data, right? Where you're just interested in the metadata, then reading uncommitted is logical because you don't really care about all the details. You really just care about the summarized views of the data itself. Whereas read committed is more for like detailed views of the data, where you're looking at the very minute details of a piece of data, and you want to show that to your user. So there's two components here, right? Read committed and read uncommitted, and we'll talk a little bit more about those as we dive more into transaction isolation levels and throughout this lecture in itself. All right, so. Right, so you can really check the isolation level in your in MySQL. And in order to check that in MySQL, all you have to do is use a query, right? So you can just say select everything from information schema dot session variables where name equals txt isolation. And what this means is that every time you instantiate a transaction, right, it writes that into the transaction, into the session log, and the session log contains a key called tx transaction isolation. And at least this is how MySQL works, right? So it writes it to that log, and then you can get the details from that log. Based on this query. So there are 4 different transaction levels: serializable, repeatable read, read committed, and read uncommitted, which is what we just talked about. And then to change the current isolation level, you just simply change the read mode, right? So you can say read committed or read uncommitted, or you can say read serializable or read repeatable read, and that will change the different transaction levels. Keep in mind that each transaction level has its own unique properties, and basically indicates to the database how to persist data to the end user through reads and through writes. And when you use these, you have to be conscious about exactly which kind you want to show the user, right? So yeah. So the next piece we'll talk about is concurrency control. A database itself must provide a mechanism that will ensure that all possible schedules are conflict serializable, meaning that that they're able to write even during the process of a read, and during the process of an update, that the data can still be written as well as be read, committed or uncommitted. So one policy itself is to allow serial schedules. One policy is to allow serial schedules, but this will cause poor degree of concurrency, right? So when you allow serial schedules, it means that you can allow for two things to write at once, right? But again, you have to manage that concurrency, and most modern databases do allow for this and has mechanisms built inside them to really maintain this kind of schedule. You can also use a concurrency control algorithm trade-off, and these vary between the amount of concurrency they allow and also the amount of overhead they incur. Finally, concurrency control algorithms are either locked based or timestamp based. So locked based means that in the algorithm itself, depending on how it's set up, it will either lock the database based on the number of reads that's being read, that's being currently run into the database, and it'll prevent the system from writing to the base until those reads are completed, or it could lock the database based on, well, not the database, but the tables in the database that are being read at the time until the updates are done before it allows a read. And this could cause a lot of different things, right? A lot of different side effects, such as sometimes the database being looking like it's sometimes a query may seem to execute a lot longer than it does because of these locking mechanisms, right? In other words, if let's say you're in the middle of a massive update of your data structure and another, your database, and another query comes in and tries to retrieve data from that. Well, that query, the update takes precedence. So, in this case, the update will take precedence. So, because of the precedence, it's going to lock that table, prevent reads from reading that table. Then, instead of taking milliseconds to retrieve the query that you're going against that database, it might take a few seconds or even a couple of minutes, depending on how much data is being updated within that database table. And also, that could look like your query is not performing up to speed, or that there might be an issue with the query itself. But really, it's because the system is doing massive updates to the database, and that takes some understanding when you become a DBA admin to really understand that these locks do occur, and sometimes it becomes infinite, right? Sometimes a poor query can cause the system to completely bog down, and it might seem like the database is crashing or something like that, right? It might even be an indicator where the database seems to have shut down and nothing's happening because of these locks. And I've designed UIs where I've seen UIs that seem to have frozen for like a couple of hours because of simply because of these locking mechanisms within the database, and the query is trying to run and execute at the same time, and it creates a conflict, and the conflict just goes on forever. So there are things like that you have to watch out for, especially when you design your database, and especially when you design queries that go against a database. Right. So the next thing we're going to talk about is concurrency, concurrency control protocols. Now, the definition here is that it is a set of rules followed by each transaction and are enforced by the DBMS to ensure, even though transactions of several transactions might be interleaved, the net effect is that the identical it's identical to executing a transaction in serial order. And what we mean by this is that even though you have 1,000 transactions coming all at once, the transaction control protocol states that each of these transactions should be occur serially, or in other words, it has to occur one at a time, right? So meaning that there's always a plan to execute these queries, and depending on the weight put on each of these queries and the amount of time it takes these queries to execute, the query optimizer essentially is responsible. Well, the transaction manager, which uses the query optimizer, is responsible to manage all of these different transactions and put them in the right order. The right order meaning that it could be it depends on your database, right? It depends how you set up your database. So the order of execution is based on a set of rules that you specify, and these can be specified through admin functions. But what it's really doing is based on the plan that you whether the plan that you set up first, whether it's having a more searchable database, and when you do have that, then reads will come first, and then updates and insertions and deletions will come after, right? Or you could just have it set up so that it's time based, right? Whatever query comes in based on the milliseconds that comes in, that one gets executed first. So you could have something that's potentially like that too. Nowadays, something like SQL Server, they have a fully intelligent schema optimizer, or concurrency control processor that actually allows them to allows the RDBMS to determine which is weighed more and which is weighed less, and based upon the user's interactions with the system. So let's say you have something like Google where you have millions of searches all at once, right? Then that would mean that the recommitted transactions will occur a lot more frequently, and those are the queries that will be optimized and will be the first to execute. Whereas your updates will probably only happen once in a while, right? The updates will only be updated when a crawler crawls through the website and then takes all of that metadata and feeds into the system. That will then be updated, but that takes less precedence than an actual search. And again, this comes back to business case, right? Because Google is a search engine, their main purpose is to optimize a search. So, and it comes back to the business. And that's what you have to keep in mind when you actually use database systems. It might seem like some functionality of that database is actually a little bit less optimized. It's because of the business rules put behind those put behind the concurrency control process, so that certain features of that database is more optimized than others. So we're going to jump into some lock-based protocols here. All right. So a locking protocol is a set of rules followed by all transactions. requesting and releasing the locks, which is what I just mentioned previous to the slide. Again, those are set based on the business rules of the RDBMS, and a database administrator would go in and actually set these up. So locking protocols restrict the set of possible schedules. And an example of transaction performing locking is that, let's say transaction 1 performs a lock on A, and then it reads A, and then it unlocks A, and then it locks B, and it reads B, and it unlocks B. And then finally it displays A plus B, okay? So, with every locking algorithm, there is a lock manager that manages these locking algorithms. So the lock manager is a module that is responsible for assigning the locks to transactions based upon the business rules that's provided. There's also lock types, and these are binary locks. Some are binary locks. Binary locks indicate that an item can be viewed and become in one of two states. Either it's locked or unlocked, right? So hence the word binary, right? So that's really easy to remember. So because of the term binary here, you only have two states, locked or unlocked. And binary locks become really restrictive, right? Because there's only two states, so you're either locked or unlocked, and there's no middle ground between. So other algorithms, other lock types are created because of this. So in our example, T1 does not need to lock an object if any. Let me move this one a little bit first. Smaller. All right, so in our example, T1 does not need to lock an object if it only reads, because two operations can conflict if only one of them is right. But there's a lot more states than that, right? There's the writes, there's updates, there's all these other different states that might not conform to this binary lock. So we'll talk a little bit more about the other states. And the other ones are, of course, shared and exclusive locks. So basically, the states that an item can be in one of these three states: unlocked, shared locked, or exclusive lock. And this frees up the transaction to do a lot more than just the binary state, right? It allows, let's say, in a shared lock, the database itself can read and write at the same time, as long as they're within the same locking mechanisms of the transaction. The two transactions are sharing the same locking mechanism. Exclusive lock, of course, is sort of like the binary lock, right? So, and then the unlocked is just basically free for all, right? And you're not locking the database at all. You're just you're allowing dirty data to be read in this case. And then finally, a shared lock by more than one transaction, if all of them can only be read. So again, shared locks means that it's allowing for some dirty data, but not all dirty data. And of course, exclusive lock itself indicates that it's exclusive just to that database, meaning that it's a binary lock. It comes down to a binary lock. So again, exclusive locks can be locked by only one transaction. Okay. So an example of binary locks is that lock Q. T1 transaction 1 locks instantiates the lock in Q, and then reads Q, and then transaction 2 has to wait for that lock to complete first. And then transaction 1 performs a Q equals Q plus 10, and then it writes Q. and then it unlocks Q, and then transaction 2 can then go in and perform its read on Q, and then its updates on Q, which sets Q equals Q plus 10, and then it writes Q to the database, and then finally it unlocks Q. So in shared exclusive locks, again, the exclusive mode itself behaves like a binary lock, right? It's just it indicates that access is reserved only for the transaction that's locked to the object, so it will perform just like a binary lock. Granted, if the operation is right, an object does not hold any other locks. Okay, and then in shared mode, it's used when the concurrent transactions only reads the object. So in other words, it allows for multiple reads into the database, and there's no updates or writes. Okay, granted if the operation is read and that the object does not hold any exclusive locks, and then mutual exclusive rule. So only one transaction at a time can own an exclusive lock of the same object, meaning that only one transaction can have So basically, only one transaction can have a binary lock to the system. All right. So a great way to view this is using a lock compatibility matrix. Again, this is all based on simple lock-based protocol, right? Meaning that there's no discrete algorithms behind there to really manage this. This is simply just locking the database and then performing a transaction against it, and then unlocking it after we're done. So this lock compatibility matrix itself, as you can see here, right? You have an S and X. So if S is so the state is only true if S is if the transaction's S and everything is false. So a transaction may be granted by a lock on the item if the requested lock is compatible with locks already held by the item by other transactions, and any number of transactions can hold the shared locks on an item. But if any transaction holds an exclusive lock in the item, no other transaction may hold any lock in the item. Just as you see in our matrix here, only if both are shared can you. Let's put a pen here. So it's only true when both shared. Sorry, I have to draw on the screen here. My fault. Give me a second. So you can see that it's only true. Oops. Did that work? Let's try this again. Sorry. All right. So we can only see that it's true when two shared locks are together like this, right? Anything else, the locking mechanism is false. So basically, if a lock cannot be granted, the requesting transaction is made to wait until all the compatible locks are held by the other transactions that have been released. So only when these the X locks here are released can it be shared again. Okay. Once the read-write operations is done, the transaction unlocks with the item, and it can then be read again. So in this example, right, we consider the following two transactions: transaction 1, which is up here, and transaction 2, and then the concurrency manager that manages this, right? So we have to lock B first, and then the transaction manager control manager actually grants B on transaction 1. And then we read and perform some operations on B, and perform some unlock on B, and then transaction 2 comes in and locks A, reads A, and the concurrency manager control then grants grants a lock on A for transaction 2. It unlocks A. Well, it reads A, unlocks A, and locks B, and then grants B on transaction 2, and reads B and unlocks B, and then finally it displays A plus B. Now transaction 1 can then lock X on A, and then the concurrency manager then grants A on transaction 2. Now transaction 1 can then read A, assign some values to A, and then writes A and unlocks A again. Now T2 then displays the sum of A and B. So assume that the initial values are A equals 1000 and B equals 1000. T2 will then display 1950, which is not correct. Now, why isn't this correct? Well, the simple locking protocol is not sufficient because a transaction may be able to access an inconsistent database state that is caused by another transaction. So as we can see here, we're already reading B when it's not when it has been set when it's been written by 1950. When it's subtracted 50 already, right? So we're displaying that before we're displaying what's in B, what's A plus B before it actually gets before the transaction of A performs its operation, which adds 50 back to A. So what we were expecting is 2000, but we got 1950 instead, which again is not correct. So because of this, if your transaction manager is not performing properly, you can end up with just situations like this where you have incorrect data being displayed. So again, T2 was able to access values that were written by T1 while T1 is still active. So the problem in the simple lock-based protocol is that a transaction releases the lock too soon. So this allows for other concurrent transactions to see the inconsistent intermediate database state, which is what we're saying here is that this display is it's occurring before we actually perform all of the other operations on A from transaction 1 here, and really the schedule should be smart enough to really move this display all the way to the very bottom here, so that A gets complete its operations before we actually see the entirety of the data. So in order to solve this problem, there's a concept called two-phase locking protocol. So it really is just an algorithm to define how transactions can acquire and release locks. So in the meanwhile, guaranteeing that each of these transactions are serializable, meaning that the writes can occur one after the other in sequential function. The writes and the reads occur in a sequential function, so that the data remains in a consistent state. So the two-phase locking rules are the rule 1: a transaction request is shared exclusive lock to read-write into a database system. And rule 2: a transaction cannot be requested by any additional locks once it releases any lock. So the phases for the two-phase locking mechanism is that 1, any transaction's lifetime consists of 2 phases, a growing phase and a shrinking phase. So in the growing phase, a transaction acquires all required locks without unlocking any data. Okay, so meaning that as the transactions come in, the RTVMS is smart enough to gather all of the locks that are indicated within that transaction, and then but at the same time it's not unlocking the data. Okay, and then the transaction is in its locked point when all locks have been acquired. So it waits until all of these different locks that the transactions are calling for comes into the system, and then until all of those locks are acquired, it will then perform a transaction lock. So the shrinking phase is a transaction releases all locks when it cannot obtain any new locks. Okay, and so the two-phase locking mechanism ensures that the preceding graph is acyclic, meaning that it's a cycle. Right. So first it begins, and the number of locks come in, and it begins. Now for phase one, it waits until all the transactions are brought in, and all of the locking protocols are brought in, and then it reaches this lock point. At that time, the transaction obtains a lock, and then after that, it waits until all those transactions are completed before it releases the lock. So once each of these transactions are completed, then it says, "Hey, we've reached the end of the locking chain. So let's release other transactions." So this maintains a consistent state between the reads and writes within the transactions. So again, and transactions lock the object before using it. When an object is locked by another transaction, the requested transaction must wait. So when a transaction is released, releases a lock, it may not request another lock. So in our previous example, what would happen then is that T1 will first lock S on A, and then reads A. T2 would then lock S in A and reads A, and then lock X on B and unlocks A, reads B, writes B, unlock B, commit, and then it would perform a lock X on C and then unlock on A, and then it reads C and writes C and unlocks C. And then finally it commits the transaction, and you come up with a better a concurrent transaction. So two-phase locking protocols ensures that it's serializable. Ensures serializability by first unlocking XA, and then writes A, and then unlocks A, while transaction 2 locks A and then writes A. If there's an edge from T1 to T2 in the preceding graph due to conflicting operation in A, there cannot be an edge from T2 to T1. So this sample here does not follow the two-phase locking protocol, right? Because first it has T1 unlocks first, then acquires lock on A, and hence the schedule does not follow the two-phase locking protocol. Right. So in this example, it shows a cascading rollback. It's one of the pitfalls of the two-phase locking locking protocol. So for example, here we have lock X on A, and then read A, then lock S on B, and read B, and then write A, and unlock A. And then transaction 6 itself gets a lock on A, a read on A, and a write on A, and an unlock on A. And transaction 7 locks S on A and reads A. So if T5 aborts, then T6 and T7 has to be rolled back as well. So this occurs because all of these transactions are all locked all at once until the final transaction happens, right? So if, let's say, if we abort the transaction of T5, then none of the reads and writes on transaction 6 and transaction 7 will happen. So this concept is called a cascading rollback because it affects all of the other transactions. So this schedule may also be unrecoverable if T5 aborts and T6 and 7 commits. So the solution to this is, of course, a strict two-phase locking protocol, meaning that a more strict rule 2 of 2PL or two-phase locking protocol that guarantees that all schedules are recoverable and cascadeless. Strict 2PL rules are: Rule 1, a transaction requests a shared exclusive lock to be read on the database item. And then Rule 2 changes. It says that all exclusive mode locks taken by a transaction be held until the transaction commits. And so the advantages of this is that it allows only recoverable cascadeless and recoverable schedules, whereas the other ones are not. All right. Well, the standard 2PL does not. And then the disadvantages of 2PL is that concurrency is also reduced because you can't do as many transactions at once. So what happens here? Well, a transaction holds locks until the end to prevent cascading rollback. So in other words, it captures all of the required transactions, and then it allows for all of the transactions to be held, and then it only obtains a lock. It only obtains a lock if the transactions are committed. Otherwise, it releases the lock instead of committing one at a time. So this allows for the entirety of the entirety of all the transactions to occur before rollbacks can occur, and that means is that nothing gets affected until everything is successful. This also means that the ability to do concurrent reads and writes within this mechanism is hindered because you have to have all the transactions commit, or none of it gets committed, which follows the rules of atomicity, but at the same time, you limit your database to perform concurrency. So what this leads to is starvation, right? Starvation is also possible if concurrency control manager is badly designed. So, for example, a transaction may be waiting for X lock on the item while a sequence of other transactions requests are granted S lock at the same time. So how do you prevent starvation? Well, concurrency control managers can be designed to prevent starvation as follows. A lock is provided for an item, Q, if there's no other transactions that waiting for a lock on Q. So consider the schedule. T3 has a lock of X and B. It reads B, sets B equals B minus 50, and writes B. Transaction 4 then locks A, reads A, and then locks B. And then finally, transaction 3 lock S and B. Neither T3 nor T4 can make a progress, right? Executing lock SB causes T4 to wait for T3 to release its lock on B, while executing lock A, X causes T3 to wait for T4 to release its lock on lock A. So this creates a deadlock. Such a situation again is called a deadlock. So to handle a deadlock, one of T3 or T4 must be rolled back and release all its locks. So the two-phase protocol itself is a protocol that ensures conflict serializable schedules. Phase 1 is a growing phase. Phase 1 may obtain locks. Transaction may not release locks. Phase 2 is a shrinking phase, which follows at the end here. All right, so the transaction may release locks. The transaction may not obtain locks as well. And finally, the protocol assures that serializability can be provided, meaning that in the between the first and second phase here, all transactions can be serialized in the order of the lock points. In other words, the transactions that the order in which the transaction was acquired, and then it only performs a release once all those transactions have completed. So two-phase locking protocols does not ensure freedom of deadlocks, right? Extensions to basic two-phase locking are needed to ensure recoverability of freedom from cascading rollbacks. And then a strict two-phase locking mechanism itself is a transaction must hold all exclusive locks until it commits and imports, and ensures recoverability and avoids cascading rollbacks. A rigorous two-phase locking algorithm is a transaction must hold all locks until a commit or abort. Transactions can be serialized in the order in which they can commit. And finally, most databases implement rigorous two-phase locking, but refer to it simply as two-phase locking. So we have to understand the differences between this, right? So older systems might just implement the locking protocol, but newer ones implement the more rigorous two-phase locking. But all of these refer to it as a two-phase locking. So you have to understand the differences between these. So, two-phase locking is not a necessary requirement for serializability. Again, it's a good process, but not a requirement, right? Because we could achieve serializability just by implementing a simple locking mechanism, but at the same time, we run into those pitfalls of rolling back and things like that. Well, cascading rollbacks, I should say. There are two conflict serializable schedules that cannot be obtained if two-phase locking protocol is used. In the absence of extra information, ordering, or access to the data, two-phase locking is necessary for conflict serializability in the following sense. Given two transactions T1 and that does not follow Ti that does not follow two-phase locking, we can find a transaction TJ that uses two-phase locking and schedules for T on TJ that is not conflict serializable, as demonstrated on the right here. So let's say lock S on B. We read B and we set B minus 50. Then we write B and we unlock B, and then we lock S on A, read A, unlock S A. We lock S on B, read B, unlock B, display A plus B. Then we lock X on A, read A, set A plus 50, and write A, and unlock A. We see that in this transaction, we end up with a faulty data or inconsistent data because we're displaying A plus B before we actually update A. So we end up with wrong data. A schedule S is legal under a locking protocol if it can be generated by a set of transactions that follows the protocol. A protocol ensures serializability if all legal schedules under that protocol are serializable. So So there's also a concept of lock conversions, right? So two-phase locking protocol with lock conversions are the growing phase. So it can acquire a lock S on an item, and can acquire a lock X on an item, and then convert a lock S to a lock X, which is basically upgrading it. In the shrinking phase itself, it can release a lock S, and then release a lock X, and can convert a lock X to all lock S. This is called a downgrade. This protocol ensures serializability. There's also a concept, RDBMS can also implement a way to automatically acquire locks. A transaction TI issues a standard read or write instruction without explicit locking calls. Now this is implied within almost every query that you make, right? If you don't specify a locking mechanism, the database automatically applies this. So, for example, the operation read D is processed as if T1 has a lock, TI has a lock D on D, then read D. Otherwise, begin if necessary, wait until other transaction has a lock X on D, and then finally grant TI to a lock S on D and read D. End. So this implementation is within almost every query that you have. If you don't specify a lock to begin with, then the system actually creates a lock for you. It wraps it in a transaction. So the operation write is also processed as if T1 has a lock on D, then write D. Otherwise, if a necessary wait until no other transaction has any lock on D. If TI has a lock on S on D, then upgrade lock D to lock X. Otherwise, grant TI to lock X on D, and then write D. So in other words, it goes through this logic to ensure that your data is concurrent within the system itself, and without you specifying exactly what the schedule is, this is built into the system itself to ensure that there are no conflicts. And then finally, all locks are then released after commit or abort. So in general, to implement locking, a lock manager can be implemented as a separate process. Transactions can send locks and unlock requests as messages, and the lock manager replies to a lock request by sending a lock grant message, or a message asking the transaction to be rolled back in case of a deadlock. The requesting transaction waits until the request is answered. Now, this can lead to a lot of problems. When you actually use databases enough, you'll see that sometimes you think that a database is performing poorly, but really it's because of these deadlocks. And if you look in the transaction manager, you'll see that there are deadlocks in the system. That's why your query is taking longer than it used to do a simple search, right? So the lock manager then is also responsible for maintaining an in-memory data structure called a lock table to record grant and grant locks on the pending requests. So this lock table can be queried against to actually see exactly what's wrong with your database. So the lock table itself has a dark. So in this example, we're looking at a lock table, right? So the dark rectangles on here represents granted locks. The light color ones indicate waiting requests. The lock table also records the type of lock granted on the request. And then the new request is added to the end of the queue for requests for the data item and granted if it is compatible with earlier locks. Unlock requests result in the request being deleted, and later requests are checked to see if they are now granted. So if transactions aborts, all waiting and granted requests of the transaction are deleted. So the lock manager may keep a list of locks held by each transaction manager, each transaction to implement this efficiently. So there's also a concept of graph-based protocols. Now, graph-based protocols are a little bit more robust, and we'll just cover the basics of it, okay? But we're not going to dive into detail. So graph-based protocols are an alternative to two-phase locking. It imposes a partial ordering of on an edge on the set of D. So let's say we have a set of D equals D1 through Dn, all of the data of all the data items. So if D points to D, then any transaction accessing both D and D must access D. Di and dj must access di before accessing dj. So this implies that D may now be viewed as a direct cyclic graph called a database graph. The tree protocol is a simple kind of graph protocol. So only exclusive locks are allowed within the tree protocol. The first lock by T1 may be on any data item. Subsequently, a data Q can be locked by T1 only if the parent of T1 is currently locked. And data items may be unlocked at any time. A data item that has been locked by and unlocked by T1 cannot be subsequently relocked by T. So just like your algorithm, your tree-based algorithms, the root must always be accessed before any of these leaves can be accessed. So again, this is a graph, but this is a simplified form of the graph, where instead of being able to access every different edge, every different item within the graph, you put a hierarchy to it in such a way that only certain things are accessed only if the parent can be accessed. So the tree protocol ensures that conflict serializability as well as freedom from a deadlock. Unlocking may occur earlier in the tree locking protocol than in the two-phase locking protocol. And finally, shorter waiting times, and this provides shorter waiting times, and increased concurrency. So protocols deadlock free, no rollbacks. It's deadlock free, and no rollbacks are required. So the only drawbacks is that the protocol does not guarantee recoverability or cascade freedom. It also needs to introduce commit dependencies to ensure that recoverability. And transactions may have a locked data items that do not access. Access. So this increases locking overhead and the additional waiting time to perform a query. And again, it also has a potential to increase in concurrency. So schedules are not possible under two-phase locking phases are possible under the tree protocol, and vice versa. So, in conclusion, we have the ability to allow concurrent transactions, which in turn allows us to improve the performance of RDBMS, right? So concurrency control protocols need to be applied in order to enforce ACID properties of transactions. Keep in mind what ACID is, right? ACID is atomicity, concurrency, and dependability, and trying to remember what the other one was. Interlopability. Yeah. No locking or unlocking too soon in simple lock-based protocol may result in inconsistent database state. So Two-phase locking protocols and delays unlocking, therefore ensuring conflict serializability. However, the two-phase locking protocols in, uh, causes other problems such as cascading rollbacks, deadlocks, and starvations. So in general, problems caused by TPL is less serious than having inconsistent data. So it's always so so what we're saying here is that even though we introduce things like cascading rollbacks and deadlocks and starvation, it's still better than having data that's inconsistent in our database, and it ensures that we can concurrently write to the database as well. So when we think about of locking protocols, we there are several overheads here, right? So the first is that management lock management has several overheads. First is granting and releasing locks. That has to be in your code for it to work. We have waiting queues for each item. We can lock granularity, attribute, role, table, or databases. So sometimes it becomes hard to trace down exactly where the lock is because of that granularity, right? And then we also have the overhead of deadlock detection and resolution. And this becomes some systems have built-in mechanisms for this, but it becomes a game of cat and mouse to find the deadlocks. And finally, lock contention for heavily used items, and this can occur in a really big database, right, where a particular sector of a market is focused on let's say your set of data, and that becomes that particular piece of that data is being used all the times. Now there are mechanisms around this, right? You could perform a caching layer to rectify this by a caching layer. Some of these caching layers, you could say, are actually widely available, such as Redis cache, right? Redis cache itself allows for faster searches because it caches frequently used items within a caching layer, and when your system goes and tries to access data, it goes through this caching layer first and finds the cached data so that it doesn't touch what's in the database. It avoids all of the different transactions that locks that could occur within the database. And this allows for the database to perform other operations like writes and reads to the other portions of the database without having to worry about without having to worry about locks on the database. Again, this becomes the way to set up Redis itself, or a caching layer itself, becomes a complete science as well, because you have to analyze your data for the pieces of data that needs to be cached. It doesn't make sense to cache every single layer of the application. Okay. All right. So the other pitfall is deadlocks, right? When two transactions wait indefinitely for each other to unlock the data. So for example, T1 accesses X and Y, T2 accesses Y and X, T1 locked X, T2 locked Y, and at the same time T1 is waiting to lock Y in order to finish, and T2 is waiting to lock X in order to finish. T1 and T2 is waiting on each other, and this performs an infinite loop that causes a deadlock. So in this example, we consider the following two transactions. First, T1 wants to write A and write B, and T2 wants to write B and write A. So the schedule with the deadlock is that T1 performs a lock on A and a write on A, and then T2 performs a lock on B and a write on B and waits for a lock on A, while T1 is still waiting for a lock on B. So how do you prevent deadlocks? Well, deadlock prevention protocols ensures that the system will never enter a deadlock state. So you can also have deadlock detection and recovery. So, to prevent it, the first protocol we have here is to require that each transaction locks all of its data items before beginning execution. Now, this might actually hinder your concurrency, but at the same time, it prevents the database from going to the state. This protocol 2, which uses transaction timestamps for the sake of a deadlock to prevention alone, it can have a wait and die scheme, which is non-preemptive. So older transaction may wait for younger ones to release the data item. Then the younger transactions never wait for older ones. They roll back instead. The would wait scheme, which is preemptive. Older transaction wounds or forces a rollback of younger transactions instead of waiting for it. So the younger transactions may wait for older ones. Both wait and die and wound wait schemes are rollback transactions. A rollback transaction is started with its original timestamp. So finally, protocol 3 is the time-based schemes. So a transaction waits for a lock only for a specified amount of time. Then after that time, the wait time's out and the transaction is rolled back. Another one, this is really simple to implement, but starvation is possible. Also difficult to determine good value of the timeout interval. Again, this comes back to analyzing your data and which transactions are more important to you based on your business rules. So, deadlocks can be described as a wait for graph, which consists of a pair of G, V, and E. G equals V and E. V is the set of vertices, all of the transactions in the system. E is the set of edges. Each element is an order pair of T connected to TJ, Ti connected to TJ. If Ti is connected to TJ is an E, then there is a desired edge from T1 to TJ, implying that Ti is waiting for TJ to release the data. When Ti requests the data, item currently being held by TJ, then the edge TJ is inserted into the wait for graph. This edge is removed only when TJ is no longer holding a data item needed by the TI. The system is in a deadlock state if and only if the wait for graph has a cycle. It must invoke a deadlock detection algorithm periodically to look for cycles. So for a wait for graph without a cycle is one in which there's no pointer back to T19. So a wait for graph with a cycle is one in which the T20 is waiting on T19. So in order to let's look at the schedule and let's see what the graph is. So let's say we have a schedule where T1 has a lock on S and a read on RA. Oh well, a lock on S on A and a read on R and read on A. And T2 has a lock on X and a write on B. T1 locks B. And then finally, T3 locks C and reads C. T2 performs a lock S. T4 performs a lock B. And T3 performs a lock A. So, does this lead to a deadlock or no? Well, so if T1 performs a lock S on A and a read on A, the lock X on A is independent of that first lock. Let's say lock S of B performs a lock X on B. T1 performs a lock S on B, but is unlinked to the lock of B from T2. T3 can perform a lock of X since the read of A is lock S of A since the read of A is already done. The lock of X of B can be performed since the write of B is done. so this does not create a deadlock. When deadlock is detected, some transactions will have to be rolled back. Basically, it's the least. Ideally, it would be the least of the transactions that affect the least amount of data, and the least important data, I should say. Now, in your business rules, there are certain pieces of data that are more important than others, right? So this again comes back to the business. Now, rollback and so you can then select the transaction as a victim that will incur minimum cost. The rollback then determines how far to roll back a transaction. A total rollback is basically abort the transaction and then restart it. A more effective rollback is only as far as necessary to break a deadlock. So starvation then happens if same transaction is always chosen as a victim. And so basically you just have to include the number of rollbacks in the cost factor to avoid starvation. So when you use these different methodologies, well, for to prevent deadlocks, well, for low, deadlock detection and recovery. For high, you basically use deadlock prevention. And that concludes our lecture for this week. I know it's kind of a short one, but again, I am out of town, and hopefully you guys are able to view this lecture before the end of class. I know that I know that I'm not sure if this will upload because the hotel Wi-Fi is pretty slow. If you're not able to get this lecture, I'll let you know. I'll check later on to make sure that it's uploaded. If not, I'll send a follow-up email to ensure that I upload it tomorrow so that you guys can view this lecture. Okay. Now, for this week, just continue working on your project, and let's see. Syllabus again. Yeah, for this week, just continue working on your part on your part 3 of your project. I know it's a pretty extensive one because of all the different things I asked you to do, and yeah. There seems to be some issues with assignment 4. So I'll address those when I come back, and then concentrate on assignment 5 and get that done. And next week, we'll take quiz 4 next week when I return, and then and I might just reduce the amount of quizzes to ensure that we cover everything. So we might not have quiz 8. And the schedule will just be shifted downwards. All right. So that's all I have for this week. Have a great day, everybody, and I'll talk to you guys later.